Now, sometimes the capacitor that you might have doesn't have quite the required capacitance. So what we can then do is maybe combine capacitors perhaps in parallel or in series. First of all, I'd like to consider what happens if we have two capacitors which are in parallel with one another. So here I have a diagram just to show those two capacitors which are in parallel. Now there are certain things we can think about. First of all, the top capacitor, I'm going to call that capacitor number 1, and it has a certain charge stored on it which I'm going to call Q1. The bottom capacitor then maybe has a charge stored on it of Q2. We can then maybe think about the capacitance of these two capacitors. I'm going to call this C1 and I'm going to call this C2. And finally, using my third colour, we're going to look at the potential difference across them. And because these are in a parallel part of the circuit, if we think about Kirchhoff's second law, then this must have the same potential difference across it as this part here. So this has a potential difference across it of V, as does this one here. Now there's an equation within the last video that says capacitance is equal to the charge stored per unit potential difference. And we can use this equation and this information here to work out the combined capacitance of these two capacitors. The first thing I can say is that the total charge stored in these two capacitors is equal to the charge on this plate added to the charge on that plate. And therefore what we can say is that Q, which is the total charge, is equal to Q1 plus Q2. So that's the first step. But then we can rearrange this equation here to say that Q is equal to CV. And using this information, I can then replace the Q's here with C times V, as so. So now I have CV equals C1V plus C2V, which is just replacing Q with being equal to CV. And what we can then note is that because the voltage is going to be the same across all of these, the V's cancel. And therefore what we can say then is that C is equal to C1 plus C2. So the combined capacitance of capacitors in parallel is just the sum of all the individual capacitances. And therefore this is a bit like the anti what we have for resistance. You've got to remember that if you have resistors in parallel, then the total resistance R is equal to, effectively 1 over R is equal to 1 over R1 plus 1 over R2. So that's resistors in parallel, but that's capacitors in parallel. What happens though when you have capacitors in series? So at the top here, what I have is my single capacitor. Now what I'd like to imagine is taking the metal plates inside it and moving them further and further apart. Now effectively the total amount of charge stored cannot increase between these two plates. But what we can do is if we move these really far apart, like so, is these will still have the same amount of charge on them. But effectively if the gap was so big, what we could then do is put another couple of bits of metal on the inside, which is exactly what I've done here. Now effectively if this has a certain amount of charge on this plate, this side of the plate will have exactly the same, but an equal and opposite amount of charge. And what we have now is we have our two capacitors which are in series. And this is what I'd like to look at in a bit more detail now. So what I can start to do is label this up. So if I call this capacitor number 1, then the charge on each plate is equal to Q1. Remember that the net charge and the whole capacitor is equal to 0, because whatever we have negative one side, we have positive on the other. But if we're thinking about the charge on just one plate, that's equal to Q1, or maybe Q2. We also know that this has a potential difference across it of V1 and V2. And again, we know by Kirchhoff's second law that V1 plus V2 is going to be equal to the sum of the EMFs around that circuit. And finally, we're going to have the different capacitances of this capacitor here, which is going to be equal to C1, and also this one here is going to be equal to C2. And again, we've got the capacitor equation that says C is equal to Q over V. So first of all, we know that this PD added to this PD equals the total PD across these two components, and therefore I can say that V is equal to V1 plus V2. Now, if we look at the equation over here, what we can say is that V is equal to Q over C. So if I basically replace the V terms with Q over C, we can say that Q over C, so the total charge of the total combined capacitance, is equal to Q1 over C1 plus Q2 over C2. Now what we can see is that if we have the same amount of charge on this plate, we must have the same charge here, and that means we've got the same charge here and here as well. And therefore actually what we can say is that for all of these things, the charge on each of these capacitors is identical. And what we can then write this as is 1 over C is equal to 1 over C1 plus 1 over C2. And this is the equation for the combined capacitance of many capacitors. And again, depends how many capacitors we might have, we could continue that equation. Now again, this is very different to what happens if we have resistors in series. With resistors in series, the total resistance is equal to R1 plus R2, plus however many resistors we might have. So if you can remember what happens for resistors in series, effectively when you have capacitors in series, it's the opposite. And the thing to note is that people often, when they look at the combined capacitance, they might get a value, but they forget to take the reciprocal of it. So remember, if you have 1 over C1 plus 1 over C2, you then need to use the inverse function on your calculator to find out the actual value of C.